Hello again. In this video, we're going to define a really useful way of writing linear combinations as a result of multiplying a matrix by a vector. And I know I've said this in a few videos by now, but a good understanding of this basic notation will be crucial for the rest of this class. First, this is a shorthand way of describing the number of rows and columns of a matrix. We say the size of a matrix is the number of rows by the number of columns it has. For example, here is a 2 by 4 matrix. So with that in mind, here's the definition of what it means to multiply a matrix by a vector. So suppose A is m by n, and we write each of these columns of A as a vector v1, v2 through vn. So for example, this matrix here has 4 columns, so you could label them as vectors like so. Now, if x is a vector in Rn, meaning it has the same number of entries in it as A has columns, then you label these entries x1 through xn. Then, Ax is the result of multiplying each of the columns of A by the corresponding entries of x and adding up the results. In other words, Ax is a linear combination of the columns of A using the entries in x as weights. Alright, now let's look at a quick example of how this works. And as usual, if you think you can handle this one on your own, that's a better way to do it, so pause it here. But I'll go through this one and part A and part B first, and then leave C as an exercise for you to do, even if you're not 100% sure. So for this one, what we're going to do is take these 4 columns, and using these entries as weights here, we're going to do 6 times 1, 2, plus pi times 0, 0, plus negative 2, which we can just write as minus 2 times 3, 6, plus 1 times negative 4, 3. And then we can just actually do the scaling of each of these vectors first. So that'll give you a 6, 12. Pi times 0 and 0 is a couple of goose eggs there, minus 6, 12, plus 1 times negative 4, 3 is like so. And then the 6, 12 plus 0, 0 minus 6, 12 is just all going to come out to be all zeros. So you end up with just negative 4, 3 is the result of multiplying this matrix by this vector. So notice for this to work, we had to have the same number of entries here in the vector as there were vectors, so that we could line them up as there were columns in the matrix. And also notice that because that we're doing a linear combination of these vectors that each have 2 entries, we end up with a 2-entry vector. And these each have 2 entries because the original matrix has 2 rows. So in general, the result of doing A times X is always in Rm, because we're doing a linear combination of Rm vectors, meaning each one of these vectors has a number of entries in it equal to the number of rows of A, because that's the way it lines up. So then with B here, let's look at this. If you try to line them up, we've got this vector we can multiply by this entry, and then this vector we could multiply by this entry, but then what do you do with the 2? This doesn't say what to do here if this n doesn't equal this n, meaning the number of entries you have in your vector isn't equal to the number of columns in your matrix. This doesn't work, so this is undefined. And for C, here's a place for you to pause it and try it on your own. The answers will show up in about 5 seconds. Hopefully you got 5, -7, 0.
Now, let's summarize the different ways we have to write a system of linear equations, such as this one: 3x1 minus 2x2 equals 3, 2x1 minus x2 equals 4, x1 plus 3x2 equals 0. The first alternative we went over was an augmented matrix like so, which again is just another way of writing the original system, but without all of the x symbols and the equal signs, just saving some paper and some ink. Then we saw how we could write it as a vector equation like so. This works because the vector on the left can be written as one big vector if you multiply the components by x1 and x2 and add up the vectors. And then saying the vector on the left equals the vector on the right is the same as saying that all three components of these two vectors are equal, which is the same thing as saying that all three of the equations in the original system are true. Now, taking that linear combination on the left and rewriting it as a matrix times a vector, a times x, we get this last version. This is nice because it reduces the whole system of equations, which in real-life applications may have hundreds or thousands of variables in equations. It reduces it down to a relationship between just three mathematical objects, a matrix A and two vectors x and b. This will make a lot of the more complicated stuff we're going to do in the class more elegant and easy to understand and easy to work with. The other kinds of notations have their own strengths as well. So for example, the vector equation is useful for doing geometric kinds of problems and understanding things that way and getting a picture of what it all means, which helps you understand things. And augmented matrix are the tools we usually use to actually solve the system. Plus, just knowing about the number of pivots and their positions in the augmented matrix tells you everything you need to know about the number of solutions of the system. So we'll be moving freely between these different types of notations for the rest of the class, so it's important to be able to translate quickly and easily between them. So we'll be getting some practice with that.